Okay, so it's time to start our introductory course on microplastic analysis. So welcome to everyone, to all the participants across the ASEAN countries. And my name is Marianne Olsen, and I'll now start to share my screen. Okay, so I hope that everyone now can see my screen. And I will, there. And I will ask my co-hosts to nod if the screen is showing okay. Thank you. So welcome to the Microplastic Analysis Introductory course. We will be carrying out this course for a couple of hours. And we will give you an introduction to working on microplastic analysis. This course is arranged by the project called ASEANO, which is an ASEAN-Norway cooperation project on local capacity building for reducing plastic pollution in the ASEAN region. And we are NIVA, our institute from Norway, is working together with CSEAS and PEMSI on this project, and it's anchored within the ASEAN Secretariat. I will shortly tell you a little bit about this project before we move into the introductory course. The ASEANO project is a project that is aiming at supporting the global goals for long-term elimination of discharge of litter and microplastics to the ocean. And the outcomes of our project is to help out finding reduction measures for key industry sectors. We are developing monitoring methods and building capacity to tackle plastic pollution. And we are studying the impacts of plastic pollution and defining measures. And also, as a part of the project, is education and dissemination. And with these pillars, the project aims at improving the capacity to tackle plastic pollution from key sources within the ASEAN region. And this course is then organized under this ASEANO project. Very short, the Norwegian Institute for Water Research is Norway's leading environmental water research institute. It was established by the Research Council of Norway more than 60 years ago, but has been a private foundation since mid-1980s. The NIVA Foundation has several subsidiaries, both national and international. And in Asia, we have an office in China. The NIVA group is almost 400 employees. And what we do is to perform research, investigations, and find solutions to environmental challenges. Today's course will be held by myself. I'll give an introduction. And then my colleagues, Dr. Rachel Hurley and Nina Toscano Buenaventura, will be giving sessions on specific topics related to microplastic analysis. So the plan of today is to start with this introduction, just 10 minutes, and then we will move into session number 1, where Nina will talk about the lab area, equipment, routines in the lab, and control of contamination, which is, of course, a crucial issue when working with microplastics. Then we will move into session 2, and Rachel will talk about extraction of particles from various environmental samples. Then both Nina and Rachel will talk about the particle characterization. First, Nina will present the visual characterization, and Rachel will talk about chemical characterization. During these sessions, it's possible for you as participants to raise questions and you can write them down in the YouTube chat box. And when we enter the session for questions and answers, we will look into what questions you have raised and try to answer them as best as possible before we end the session and this event with some concluding remarks, and also what we will present what may come after this introductory course. So let me take a brief look at the situation around plastic litter and particularly on the microplastics. The situation is that there is really no historic data on plastics. The attention has been increasing, and for the last 10 years, we have been aware that this is a potential threat to the environment. But there is little data to look back on, and given this, there is also no really baseline data for plastics in the environment. That goes both for microplastics, but also for the larger items, the macroplastics. It is also the situation that even though there has been a lot of investigations and studies on plastics in the environment, it is not yet included in any regular monitoring programs. This is something that we already now see coming, and for sure it will come in the years ahead. So what is also the situation is that there is a lack of standardized methods and also systems for quality assurance. Most of the studies that has been carried out so far with regard to microplastics has focused on the documentation of microplastics in various environmental compartments. But comparing across these studies is still quite difficult and a challenge due to this lack of standardization. And it's also little known still about the effects on both human and environmental impact. And also about the knowledge, or there's a lack of knowledge on fate in the environment. And due to these two bullet points here, there is also a lack of understanding for what is actually the environmental risk of microplastics and plastics in the environment, and what is the threat to human health. So in order to address these questions and understand better the impact and the effects, it is crucial that we still continue to work on standardization and harmonization of methods. And indeed, many initiatives are ongoing within nations and internationally. So later in this event, we will now be looking into more details of how to carry out microplastic analysis. And in general, the situation is that doing microplastic analysis, for those that have not yet had any experience in this field, I would just like to say that this is nothing like when you want to do a chemical analysis, where you can basically deliver your sample to a lab and get a concentration back. So in order to analyze for microplastics, there is a need to extract the particles from your environmental sample. And the steps in this procedure is that you have to purify your sample, extract the particles, filter, and then you can start identifying the particles. And these are details that we will come back to during this event. During all steps of the microplastic analysis, the contamination control is crucial, and this is also a topic that we will come back to. Particles and plastic particles are everywhere and can't really be completely avoided, but we need to try hard during our procedures to avoid the contamination of samples. So this was a very, very quick and short introduction. And I will now give the word to my colleague, Nina, and she will start presenting the introduction to the lab area, the equipment, the routines, and the control. So I will stop sharing my presentation, and Nina can prepare and will start presenting hers. Thank you, Nina. We can now see your presentation. And if you also have a full screen, then everything is ready to go.
There we go. Thank you.
Thank you.
So this session will touch upon the basic routines, like Marianne has mentioned, the routines of the lab, some of the equipment we have, and contamination control. So we will continuously talk about contamination and how to control it and how to detect if you've gotten contamination in your samples. So this is very necessary for microplastic analysis. But first, it's important to state that microplastics are everywhere. It's impossible to avoid using plastics or not being surrounded by plastics, even in our lab, as you can see here. So plastic is what we wear, from clothes to shoes. Lab coats are made to last longer. It has a polymer blend of maybe cotton and PET. From instruments we use to lab, so it's very, very important to try to limit the use and be aware that our surroundings, even in a clean room, can contaminate your samples. So one of the first routines we have is to avoid contaminating our samples more than is necessary. So even before opening our samples, we routinely use a lint roll for our cotton lab coats. This removes excess fibers from your clothes. And that's not the only thing that can contaminate your samples. It's therefore important to exclude other plastic fibers from dust. So dust efficiently wherever you are. This applies to your bench tops where you work, your sink area, even your microscope that you use. Basically any surfaces that is in your working environment. So with this in mind, you also need to ensure that all the solutions that you have are pre-filtered, like you see here. You do this by filtering either your Milky water or RO water in the lab. So this ensures that the inside of your filter apparatus is clean. You then have filtered water to use for your samples. And if you are going to use other solutions, such as density separation solutions or hydrogen peroxide with your samples, these also need to be pre-filtered, as well as your filtered water before adding them to your samples. So other routines we have with our glass equipment is we burn them in an oven and rinse them 3 times with our filtered water before we have any samples in them. And after rinsing them, we cover them quickly with aluminium foil just to prevent any more contamination. It's also preferred to work with your samples in a clean environment, and I will continuously say this throughout my session. Preferably work in a laminar flow bench or a fume hood. If this is not possible, try to limit the amount of people you're working around with when you're working with your samples in an open space. The more activity there is around your environment, the more likely there will be atmospheric contamination into your samples. So before starting the process, we also need to think about how the particles will actually be chemically analyzed. So we have in our lab a micro FTIR. So we process and filter our samples to fit our instruments and its accessories, as you see here. This determines the type of setup and filter you need, but Rachel will talk more about chemical analysis later on. So some of the basic equipment that we have, as I've mentioned, is our FTIR. We've also got, as you see here, the Buchner glass filter apparatus. We've also got a plastic rare polymer called polysulfonalgene filter apparatus. The reason why we sometimes use this is so that we can filter more samples time efficiently in one go. You also need glass fiber filters or anodiscs or silicon or steel filters, whatever your chemical analysis instrument would need, including petrodistors for protecting your samples. So this is an example of how we work. It's a filtration setup with the polysulfonalgene filter apparatuses in a laminar flow bench. So this flow bench purges the inside of the compartment for about 3 minutes before use and has a continuous airflow that flows downwards to avoid more atmospheric contamination in the samples, keeping it to a minimum. So this setup, as I mentioned earlier, allows us to filter multiple samples at the same time. If you look more closely, we have fitted colorful red rubber hoses between the individual filter apparatuses. So this is to ensure that if our samples will get contaminated by rubber hoses, it would be very, very apparent in our samples during visual characterization. Likewise, we have the plastic polypropylene bottles fitted to our RO water bottle. Oh, sorry. There we go. Here you see, to the right, you see water samples in their aluminium container and paper lid foils. This is to protect the samples from the environment. And under the left arrow, you see 3 beakers containing filtered RO water. These have also been burnt and pre-rinsed before use. So these filtered water are to be used to rinse the tweezers after every use when we grab the pre-checked filter papers. So to the right, you see the pre-checked filter papers in their petri dishes ready to be used. So these, we pre-check them under the microscope. This is to ensure that there are no contamination from the filters. If they've got particles or fibers from the manufacturer, we remove them with steel tweezers. So this applies to any other filters that you might use for your samples. So if it's a steel filter, you would preferably, if they can, be burnt in an oven, or you can use an ultrasonic bath to remove any contamination. So the microscope we use is quite a basic one. This is a stereo microscope. It has an attached camera on top for photos, an external light source to shine down on the particles. So this microscope can magnify to up to times 50, but we use up to times 20 to take pictures and measure. So this is sufficient for particles to about 50 microns. You don't really need more than that. But if you find it difficult in the beginning to look at your samples with times 20, start larger at either times 10 or times 6.7, and then zoom in at a later stage. For samples that you receive, it's important, if you're going to subsample, to homogenize your samples. So with water samples, they can be stirred or mixed, but not with soil and sediment. So this is a riffle box that mixes soil and sediments samples very thoroughly. So you pour your samples on top. The sample is then divided into 2 parts in the tin boxes at the bottom, and then you repeat the steps to homogenize the samples that you have received. For contamination control, as I've mentioned before, if possible, do it in a controlled, clean environment like a lath bench or a fume hood to minimize airborne contamination levels. One can also work on a bench top, but be sure that everything is, all your samples is covered and there's little activity around you. Also, make a list of possible plastic contamination that can end up in your samples, like if it's a glove or the polypropylene bottle. Note down the type, the brand, polymer type. Same goes for the vacuum hoses, squeeze bottles, etc. So this is a picture of one of our procedural blanks. This is a way for us to check if we have managed to contaminate our samples with either cellulosic fibers or any plastic particles. This is basically, a procedural blank is basically a lab blank. It's taken in the lab, unlike the environmental samples. And it doesn't contain the sample, but in our case, we use filtered RO water. If you've got milky water, use that. So this procedural blank is processed and it goes through all of the same steps as the environmental samples. And it's used to assess contamination from the lab side, such as airborne contamination, like I've mentioned before, dust, fibers from clothes, particles introduced by using plastic utensil products in the lab. I know I'm repeating all of this, but it's very important to remember all that can contaminate your samples. And if possible, introduce reference materials into some of your samples. So these are large pellets and beads up to about 1,000 microns. These spike samples have the same type of matrix as your environmental samples, but are known particles to you. It could be one type or several types. You should know the polymer composition, mass, or number of particles that you have spiked your samples with. So these samples also undergo the same processes and treatments as your environmental samples, so that the processes that are used for extracting your microplastics will be assessed for how precise and efficient they are. So ideally, if you use reference material or spiking your samples, you should resemble the size and morphology that you would expect in a sample. So if you're looking at above 300 micron samples or particles, then preferably you would have materials from 300 and above. So if you're looking at both fragments and fibers, include both. But if you're only looking at fragments, then you do not necessarily need fibers. Thank you.
Thank you, Nina. And after this, Rachel should be ready, but we have a couple of minutes, and I would like to ask you a few questions, Nina, that you may share to sort of share your experience from working in the lab. So you have been talking about contamination of samples, and you also said that it is important to have colors so that you can actually recognize if there is any contamination, and you can see the colors. So could you explain a little bit more in practice what this means? You said that you had this red rubber on some of your bottles there, but does it also have an effect on, for example, what you wear, the gloves you wear, the clothes you wear? Can you give us some example?
Very much so. So we try to have the clothes underneath our lab coats. We try to have slightly more colorful clothes, just so that we know that that day of processing our samples or visual identification, we will have that specific type of color, so that we can backtrack that if we see a lot of or some of the same fibers or particles that may contaminate. We also note them down. So we're quite thorough of what type of clothes or even any type of equipment that we have in our lab.
Thank you. And now we have not been talking about the sampling procedures, but of course this is also important to think of during sampling, so that if people that are out in the field taking water samples, sediment samples, and so on, have any kind of clothes, or obviously they have clothes, but the clothes that they have should also have colorful, they should be colorful in order to actually be able to recognize if there is any contamination. Isn't that right?
Exactly, and that will also be reported back into the lab, so that we have a list of what the clothes people that are sampling our samples have been wearing, including the polymer type, if it's been cotton, or if it's been PET or acrylic, polypropylene. Yeah.
Yeah. And also when samples are received in the lab, they may be in a package, which is very often also some kind of polymer. So you do take some precautions to this also, I know, to make sure that you have control of the potential contamination from the packaging. Isn't that right?
Yes, that's correct. So we also FTIR those packages, even if it's a glass bottle with a blue plastic top. We scrape off a little bit and we FTIR that as well, so we can match that specific type of plastic if we find a few of those in our sample.
So my last question, Nina, now is what would you say is of most concern? What is the typical item or textile that potentially gives most contamination in our lab?
In our lab, it will be fibers. Thankfully, we have been very strict and diligent about dusting and cleaning, using a very important tool, the lint roller, on our lab coats. So we find very little, but we find mostly cellulosic fibers.
Yep. Great. So this simple little tool, the roller,
Yeah.
that is maybe the most important equipment that we have in our lab. Is that so?
That is correct. It's very basic and simple, but it does the job.
Thank you, Nina. Then we will move over to the next session, which is about the extraction of particles from various environmental samples. And Rachel will give this session and explain to you the differences between working with the various environmental samples. Okay, Rachel.
Thank you very much. Yes, I'll be talking about how you go from having a sample that has been delivered to your lab or that you've collected in your field to some microplastic particles such as these here on a filter. So, first slide. Microplastic contamination has become a hot topic, and microplastic particles are increasingly being reported in all corners of the globe now. There is some concern about the exposure of humans and organisms to these small particles, although the subsequent impacts of this are unknown. The search to investigate just how far this contamination has reached has led researchers from around the world to search for microplastics in a very wide range of different matrices. This includes all environmental matrices, from the seas to lands to even air, and microplastics have now been found in even very remote locations around the globe. Several investigations have also looked into the occurrence of microplastics in what we eat and drink, with the aim of establishing an estimate for human exposure. Studies have reported microplastic particles in drinking water, alcoholic drinks, edible salts, seafood, fruits, vegetables, and carbonated beverages. We are also now seeing that microplastic particles can come from the things that contain what we consume. So we've seen recent examples from milk bottles and tea bags. Whilst the actual effects of this exposure are still unknown, researchers have an interest in investigating more and more sample types for microplastic contamination. This introduces new challenges for extracting microplastic particles. All of these sample types vary widely in terms of their properties. So how much moisture they contain, how much organic content there is, and whether there's the occurrence of resistant compounds or dense solid matrices such as sediments. There is no single technique that is capable of quantifying the microplastic content of this full range of sample types. Instead, particles must first be isolated from these matrices, and we need different approaches to tackle each one. This presentation will provide an introduction to the different approaches that can be used and how we can prepare our samples for visual analysis and chemical characterization. So to kind of narrow that list down, I'm going to focus on some of the more common sample types. These are 5 categories of environmental samples that are very often the focus of microplastic studies. They are clean water, and this is water with very low or organic or sediment content, such as drinking water. Clean sediments, so this is any sediments that have kind of very low organic content, such as, for example, a beach sand. Then dirtier water, so water that has higher organic content and usually a sediment load, such as river or seawater. We also will look at dirty sediments. These are sediments with a high organic content, such as soils, river sediments, or marine sediments. And then finally, biota, such as tissue from blue mussels that are pictured here. Here we see those 5 examples shown with the broad approaches that are required to purify these samples prior to particle extraction. In order to achieve a filter that has microplastic particles ready for analysis, such as those on the bottom row here, we need to take 1 or more steps to reduce the sample volume and also separate particles from sediments and to remove or reduce the organic matter content. Some samples require few steps, whilst more complex sample types must be subjected to multiple processing steps to prepare the microplastic sample for analysis. We'll start with the easiest sample type first in terms of processing, which is clean water. So water samples that do not contain very much sediment or organic content can simply be filtered to reduce their volume and isolate the microplastic particles. This is typically performed using vacuum filtration, where a vacuum pump sucks out air of the lower parts of the apparatus here, and the water is quickly pulled through the filter. Microplastic particles will retain on the filter, as shown here, and the water in the chamber below can be discarded. We've extracted all of the microplastics that we can from that water. The size of the particle that will be collected by the filter will depend on the pore size of that selected filter type. However, the lower the pore size, the slower the filtration rate will be, especially if there's any impurities in the water sample. Following filtration, the filter can be removed from the apparatus and saved for analysis. The type of filter that you should use for your microplastic analysis will depend on what type of visual analysis and chemical characterization you plan to undertake later on. For example, if you plan to perform visual analysis prior to chemical characterization, such as FTIR, we use Whatman glass fiber filters, and these are very commonly used. Here at NEVA, we prefer to use the GFA type, and we typically use a diameter of 47 millimeters. This provides a large area for observing the particles and has a light background for identifying and documenting the different particle types. With the GFAs, the fiber weave is actually quite tight, so it's easier to pick the particles from the filter for subsequent chemical characterization. If you're planning to use a more advanced or sort of automated approach, such as using FTIR imaging, you should ensure to select an appropriate IR transparent or IR reflective filter. Some examples of these suitable filter materials include silicon, silver, or aluminum oxide. This analytical technique facilitates detection of very small particles. So we can go down to around 10 micron with this technique. And so the pore size of these filters should also be correspondingly small. If you will instead use, for example, a mass spectrometry approach, you should choose a filter that will not interfere with the plastic signal when you're running analysis. Here at NEVA, we usually filter onto a small glass fiber filter, usually with a diameter of around 13 or 25 millimeters. And we collect the particles on those and then fold that up carefully to place into a pyrolysis cup for analysis. Okay, so that was clean water. Let's move on to slightly more complex samples. And we'll first talk about the separation from sediments. So this is very apparent when we have sediments such as a beach sand sample, where there's very obviously a lot of sand particles, or dirty sediments where we can see lots of sediment particles. But it's also relevant for samples such as dirty water, because you might have suspended sediments, particularly very fine ones, in that water as well. So we still need to deal with that mineral component there as well. So a few different techniques have been used to achieve this sediment separation. Some of these include elutriation using air and water, or the use of electrostatic devices. But by far the most common approach is to perform separation using density. This uses salt solutions, typically at their saturation point, to float out less dense materials, including the plastics. Most common polymer types that are used in products and found in the environment have a density of between 0.8 and 1.6 grams per cubic centimetre. Sediment grains are more dense, typically around 2.6. That's with quartz and silica. Therefore, we can use solutions with densities between these two values to extract microplastics from the more dense solid matrix. There are many different salts that have been used in microplastic analysis to achieve this. For example, sodium chloride, calcium chloride, zinc bromide, sodium iodide, and sodium polytungstate that are listed here. The maximum possible densities of these solutions do vary. The more dense solutions seem like a more attractive approach because we can extract more of the plastic particles, but they are much more expensive, and some of them are actually toxic to humans and the environment. So you have to consider the safety as part of that. You can use obviously cheaper and more accessible solutions such as sodium chloride, but you must consider that this won't extract the full range of potential microplastic particles, because the 1.2 grams per centimetre cubed, that doesn't cover the full range of plastic types. So you may not actually be extracting everything with that. So there's a trade-off to think about when you're selecting the density solution. To undertake density separation, the salt solution should be added to a suitable container along with the sample. Remember to pre-filter the solution before you use it each time, as it may contain some microplastic contamination. You should seal the container and agitate it vigorously for 1 to 2 minutes, or until the material is very well mixed into the solution. If you have some very fine-grained sediments, it might take a bit longer to make sure you've really wetted all of that material and got it really, really mixed. So keep an eye out for that, and you should just look at your sample and make sure that you're happy with how well mixed it is. After that, you want to sit your container down and let it sit undisturbed for typically around a day, until all of the solid material, all of those sediments have settled out and the liquid above is clear. If you have some very coarse sediments, this might be quicker than a day, but if you have a sample with, for example, some silts and clays, it might take even longer. You might have some cloudy liquid above your sediments. For a few days, you need to wait for all of that to settle out before you proceed with the next step. So once you've got your clear liquid, you want to carefully decant it and filter it as you did for your clean water samples. You want to make sure that you don't disturb any of that solid material at the bottom, because that is the bit that you're trying to separate out. So when we're using these density solutions, we're using densities that will extract the microplastic particles. And so they should all float to the surface of the solution when we undertake this process. But if you have a complex sample, some of them may get trapped in those heavy sediments, even though you've agitated just when they're settling out. Therefore, it is recommended to perform at least 2 extractions with the density solution to isolate the majority of the particles. This means repeating the process that I've just described twice in order to make sure that you are recovering the majority of the microplastics in your sample. Okay, moving on to the organic matter removal now. So this is obvious for samples, for example, biota, where we have biological tissue, but it's also likely that we will have organic content in river water samples, soils, for example, that we also need to deal with. We need to use an additional step to remove the organic material, as processes such as density separation cannot do the job alone. Organic material typically has a density of around 1 to 1.4 grams per cubic centimetre, and this is within the range of the target microplastics. So when we follow the density separation process, the organic material will also float to the surface of the solution, and that can interfere with analysis by concealing the particles whilst we're doing visual analysis, or coating the particles and preventing effective chemical characterization. So you must try to remove or reduce this organic content of the samples before proceeding with the processing. Several different protocols have been tested for microplastic analysis. Different approaches for removing the organic content, including peroxidation, that is digestion with hydrogen peroxides, alkaline digestion, for example, using potassium hydroxide or sodium hydroxide, Fenton's reagent, which is hydrogen peroxide in the presence of a catalyst, acid digestion, such as with nitric acid, and also enzymatic digestion to remove different organic fractions have been tested. For example, with the last one, cellulase can be used to remove the cellulose, and it's usually done in sequence to address each different type of organic material in the samples, and that's what the sequential bit means there. Whilst the goal of these different procedures is to remove or reduce the organic content, it is very important that the preservation of the polymers is also central to the selection of the procedure. It is important to use an approach that does not damage, degrade, or remove plastic polymers along with the other plastic material. So that's something that we need to consider. Different sample types that contain organic material in different forms may be more or less difficult to process. Typically, samples that contain only a small number of different types of organic material and in larger sizes are easier to treat. For example, number 1 here presents an example of beach sand that contains large fragments of plants and seaweed, for example. This can simply be sieved to remove the organic material because it's a lot larger, and then we can just check that sieve for any plastic material that's sieved out, and then go ahead and treat our beach sand as clean sediment. Samples that contain more complex organic materials, such as biological tissues, require digestion steps to liberate those particles. When there's organic material present in different forms, so we have, for example, biological tissues, but also cellulose, chitin, things like this, we need multiple steps, often using different reagents to extract those particles. So as we can see, even with samples that contain organic material, there's still no one-size-fits-all approach to handling these sample types, and we need to consider what is in our samples when we decide what the analytical process should be. So we've tested some of the different approaches here at NIVA. We observed that some of the digestion protocols that are used in other examples to remove organic material, not necessarily in microplastic analysis, when these are used at high concentrations or high temperature, it is possible that it can damage plastic particles. And we can see some examples here where the surface of the particle are damaged after exposure to the different reagents, or the size of the particles are significantly reduced, so they've been reduced in size. This damage can also follow the particles into chemical characterization. The degraded plastics may not register in the same way, and the polymer type may be misidentified. So we can see here that there's some differences in the spectra as a result of these degraded particles. So it's very important to check that protocols preserve the microplastics that you're trying to analyze. From our testing at NIVA and also in the wider literature, we found that enzymatic digestion and Fenton's reagent are both safe for particles, at least down to 50 micron in size. The use of hydrogen peroxide or alkaline solutions is also considered safe, so long as safe temperatures and concentrations are observed. Acid digestion is not safe for particles, as acids can destroy a wide range of different particle types. There are only some specific examples where acid is still used for microplastic analysis, and that is for very complex samples. So, for example, fish stomachs that contain a lot of different types of material, as well as lipid-rich biological tissue, they typically require some form of acid digestion in order to be able to get to the small microplastic particles. This will likely destroy some polymers, but when we use this technique, we can at least confirm the presence of some polymer types in these sorts of samples. So we can see there are some specific applications where some of these techniques are still used. Due to the very wide range of different matrices that have been investigated for microplastic particles, and also which have very different properties, There is no one-size-fits-all approach to extracting these particles. You should consider what all of the non-plastic components of your sample are and how these can be safely separated or removed in order to isolate just the microplastic particles. Remember that preservation of these plastic particles is key and essential for analysing the full range of microplastic contamination. The best approach that you can follow is to try out relevant protocols on a test sample before you get started with your real samples. This will ensure that your selected approach works for your specific samples and not just similar samples in the literature. If this is not possible, you should take particular note of things such as digestion times, concentrations and temperatures of different protocols that have been used before. These are all very important. The density solution selection should consider the target range of polymer densities, and the sample to solution ratio should also be considered. So take a note of that when you're looking in the literature for protocols that you can use. Finally, just some general points about sample processing and particle extraction in general. An important point to consider is the size of your samples. When you're undertaking the initial sampling, you should ensure that you take a large enough sample to capture enough microplastic particles to be representative of that environment or of that particular matrix that you're looking into. The ideal scenario is one where you are able to do some initial testing, as mentioned before, and then you can kind of establish what works for your sample and what levels of microplastics you find before you then undertake your full sampling program, so that you can then adjust your sample volume or sample size, for example, after that. When you're taking subsamples of a larger sample, you also need to make sure you are being representative. So we do this by making sure we homogenize our samples very well. So Nina touched on this with the riffle box that we can use for dried sediments or soils. And so we want to make sure that the sample is very well mixed before we take those subsamples. It's very often observed that microplastic contamination is very heterogeneous, so we want to try and remove some of this heterogeneity before we take our subsamples. Even though we've done that, there's likely still to be some differences between the subsamples we take, so it's very important to take replicate subsamples, ideally at least 3 per sample, to make sure that you capture the full range of that difference. And finally, you want to take subsamples that are of an appropriate size so that the number and the mass of microplastic particles are, allow you to achieve good statistical robustness without adding too much analytical strain. So without having too many particles that you need to visually analyze or chemically characterized. Finally, with all your sample processing, you should include 3 blank samples and 3 spike samples with each batch of samples that you process. Blanks are now considered to be a minimum requirement for publishing microplastic data, but spike samples are actually increasingly being seen as a very important component of ensuring good quality assurance and quality control in microplastic analysis. The blank samples check that you haven't added anything new to your samples. So that is from background contamination, for example, from the laboratory environment or from sample containers or apparatus. The spike samples help to check what proportion of the total microplastics you have successfully extracted. And this is known as extraction efficiency. So together, this gives a good idea of what the original microplastics, so kind of the microplastics that were in your sample originally, what the picture really looks like. These samples should follow all of your real samples along the full analytical procedure, including all of the processing steps. So treat them as your real samples. Thank you very much. That's everything for extraction of particles.
Thanks a lot, Rachel. And before we move on to the next session with particle characterization, looking more into how to do the visual and the chemical, I would like to ask you just a few questions. So obviously, as you also showed, some matrices are quite easy. There are some that are very difficult and challenging to work with. What would you say is the most challenging that we have had experience with in our lab?
I think fish stomachs are definitely very difficult, especially if you have a larger fish, because they, if it's a predator, for example, their stomachs can be full of lots of different types of materials. So you might actually have smaller organisms inside the fish stomach that you also need to deal with. And there can be lots of very resistant forms of organic materials, such as cellulose and chitin, that is inside those stomach contents. And then you need to deal as well with the stomach coating, the kind of the lining of the stomach, where you could also have some microplastic particles. So you also need to deal with those proteins and those fats as well. So there's just a lot of very resistant organic material types there, and you need to introduce lots of steps that then can potentially damage particles. So that is definitely very complex. Also, different types of food are also difficult to deal with because the particles are generally contained inside as a result of kind of the process of producing that food. It's sometimes difficult to make sure that you get all of those out. And food samples aren't typically digested in labs in a way where they just remove all of the organic material and leave plastic. So there's not a very wide range of protocols yet in the literature to sort of safely deal with those. So they're still quite challenging.
Yeah, and I know that we have worked on fish feed, which was maybe particularly challenging. Okay, we can come back to this, and we have also gotten some questions, but we will try to answer them when we come to the question session. So then we will move on to session 3 with particle characterization, and I will give the word to Nina, who will start out talking about visual characterization, and then Rachel will continue on the chemical characterization.
Thank you, Marianne. So after you've processed your samples, what happens next? You've got your sample on a filter paper, and you're about to do visual characterization, if that's what you will be doing. If you've got pyrolysis, like Rachel have said, this step will not be necessary. But for us, this step is necessary due to our FTIR. So ideally, you would want to traverse your filter, covering the whole of your filter. So we usually use a 47 millimeter GFA to investigate, to filter our samples on. This is for investigating suspected microplastics. So if you follow the arrows, you're traversing the filter, as you see on the image, and recording the particles. So this can be done in several ways, but this is 2 of them that we find effective in our lab. So this is by one, circling the particles on the actual filter paper, one by one, or by gathering together to minimize the number of pictures that you will be taking. So you literally pick the particles, tweezers, one by one, and then gathering them to a place on your filter paper, and then taking a picture. So once you've gathered your microplastics, like you see in this picture, keep this color scheme very simple. So one of the first things you see on your sample will probably be the most notable ones, which are the very visible colored ones. When you're recording your colors down, be very diligent about not writing light blue, turquoise, or fuchsia. I've seen a few spreadsheets where they've done that, and you don't really know which color scheme to put on. So if you've got light blue, put it as blue. If you've got pink, light pink, put it as pink. But you also see eventually white and transparent ones. So here you see an image of that we've taken of some reference materials. And once you've taken your pictures and calibrated your camera for your microplastics, here at NIVA, we use the ferrite diameter to measure our particles. So this is done by measuring the longest and the shortest dimensions, as you can see from the fragments and the beads on the pictures. However, the fibers we measure them along the center of the fiber from end to end, as well as the diameter. So this makes it a bit more accurate instead of just drawing a straight line from end to end. And also categorizing the morphology of the particles can be a little difficult, because when I first started out, I thought, well, aren't all particles broken down? But usually the broken down particles are very visibly torn off. So we would put them as fragments. And as you see, large pellets would be large pellets. Spheres are round, also fibers. But after participating in several interlab calibrations, we have seen that slightly different institutes vary their morphology registering. So as long as you are consistent with how you categorize your particles, that will be fine. There are guidelines, but there are no set rules. So we have also managed to find our own guidelines at NIVA to distinguish between cellulosic fibers from plastic fibers. Again, this is guidelines. This is not like a set rule, but the usual signs are uneven colorings. Like you see, there's one of the fibers are very dark in the middle, but light at the ends, almost translucent. They don't really have much shine to them. They're matte or dull in color. The diameter also changes in thickness, and the ends are tapered or split in several places. They can have 2 splits or even more splits than that. Usually plastic fibers don't have those types of signs where they are very frayed at the ends. So again, these are just guidelines, and this can vary, but it's important to try to eliminate the non-plastic fibers if you are going to analyze these. So this is an image from a fish inside a fish stomach that we filtered. These are what we first call suspected particles until we've actually chemically analyzed these. So the 2 fibers here have been FTIR'd. The gray one is polyester and the blue one is polypropylene. It may be a bit difficult to see from this picture, but these have a shine to them. They're also uniform in diameter, and they also have really clean cut ends. So these are the things that we try to look for to see if they're most likely plastic polymers or not. So on the top, you see fragments, black rubbery particles. So if you squeeze them or prod them with your tweezer, they easily bounce back to their form. The pink fragment is hard, but it's not as hard as mineral or small stones, so it's slightly softer than that when you squeeze it. And not all microplastics have big bright colors, as you've seen, like our reference materials. Some are white and translucent and may be more difficult to detect. And that's why it's very important to try to handle the particles during visual analysis. We advise people to first go to the larger microplastics with your tweezers and try to just have a feel with the tweezers on how they act and how they maybe sound, and then progress to even smaller. So that this skill, this visual analysis and moving and picking up particles is very time consuming, and you need time to finite or be skilled at this task. It takes a long time. So especially in the beginning, you will most likely lose particles, even larger ones. So do trial runs on non-important samples first before you start with your proper important samples. Also, when you take a picture with your chosen program for your camera, if you have a lot of particles in your picture, we usually number particles. We take a second picture and number the particles so that you can distinguish them from one another. It is also easier to find and locate them on a later stage, and including your spreadsheet later on. It's also important to have a little bar. So if you have a look at the bottom right corner, we have, it says 1,000 microns. So you can basically see how large these particles are at a later stage. And this picture is taken at a magnification of 20, so it's not very, very zoomed in. So this spreadsheet might be a bit daunting. So after you've selected your suspected microplastics, they need to be recorded. So this sheet has been cut out from a larger spreadsheet. So I'll take you through it. So the first thing we note is the processing date. So we can backtrack that to the samples that have been processed. We also note the scientists that have visually analyzed the samples, the station and site, if applicable. If you look down, there's a lot of X's. That is because the samples were anonymized. We did not know where the samples came from and where the sites and stations were taken. That's why there are X's and numberings downwards in sample ID. We also number the particles from 1 and upwards from each station or site. But this is up to each individual to decide if that's how they would like to record the data. This is just an example of how to record the data. We have experienced that the more information, the better we can backtrack if we have any questions later on. Also, remember to note down the morphology type, the color, the measurements, and we also include comment columns just in case we have something we would like to note down, to remember, come back to, or just anything if something went wrong. The last columns are for the chemical polymer composition. So as we use our FDR instrument, we get matches from 0 to 1, where 1 is a 100% match. So this is an example of how we have recorded a fiber from a sample. We have the date, the station and the site, and the morphology fiber is noted. The blue color, length, the shortest and the longest length in microns, and the polymer type and the FTR match. Thank you.
Thank you, Nina. And then Rachel will continue with the chemical characterization.
Yes, I'm just going to share my screen now. Okay, here we go. So first of all, it is important to state that there is no single instrument that can simply determine the microplastic content of a given sample. There's no machine where you can insert an untreated sample and receive microplastic data out from it. So instead, we have to adapt some existing chemical characterization techniques in order to obtain microplastic information. The aim of chemical characterization is to identify the polymer type of the particles that we have extracted and characterized through visual analysis. None of the steps up to this point, so none of the sample processing steps or all the visual analysis, can provide information on what type of plastic your microplastics are made out of, or whether they're actually made of plastic at all. So we need to include this step to confirm whether we have microplastics and provide additional information about their polymer characteristics. I will briefly introduce some of the different instruments that have been used to chemically characterize microplastic particles. So the most commonly utilized approach is vibrational spectroscopy. Specifically, this is Fourier transform infrared and Raman spectroscopy. These machines use beams of light, either infrared or monochromatic lasers, and then the absorbance, transmittance, or the reflectance of this light, depending on the technique you're using, that is registered by the instrument to determine the material composition. Other approaches include mass spectrometry techniques. Gas chromatography mass spec, or GCMS, is the most common approach here. It's necessary to first transform your samples into a gas, given the name, before they can be analysed. This is typically done with a pyrolysis unit or thermal desorption unit to heat up your samples and convert them to gas before they can be conveyed to the GCMS and analysed for polymer content. Finally, there are other techniques which can also provide information about polymer types, but are less widely used at the moment. So these include, for example, differential scanning calorimetry and also laser direct infrared imaging. So none of these mentioned techniques have been specifically designed for microplastic analysis. And actually, microplastic analysis is not the most important use of many of these machines. That means that not all forms of analysis using these techniques are appropriate for the analysis of plastic particles. For example, FTIR analysis can be undertaken in many different analytical modes, and different accessories are required for this. So if we're looking at large particles, ATR, FTIR, which stands for attenuated total reflectance, that's what's required. That's what's recommended for polymer analysis. We can see an example of this on the right of our instrument here. This uses a vise to provide good contact between the polymer particle and a crystal, and then the machine analyzes just the surface of that particle. And there are other accessories which can be used in this instrument, but these are less well suited to plastic particles. When we use this ATR approach, we can only go down to around 300 microns, and it can get a little bit fiddly the smaller that you go, because you need to individually pick your particles from another filter and lift them to the crystal for analysis. So when you're getting down to 300 microns, it ends up being quite careful work. And some of these things are also the case for Raman spectroscopy too, as well. So we need to consider what is the best approach for these. For example, if we want to go below 300 microns, we need to have a microscope attachment. This is then converts our instruments into a micro FTIR or micro Raman. And this helps us to view the smaller particles and then target the beam of light at them in order to measure them. So we need to consider not just whether we have access to these instruments, but also what techniques are available for us to undertake chemical characterization of the plastic particles. The limit of detection for these techniques is determined by both the analytical modes that are used and the overall approach. The sample processing that you perform prior to chemical characterization may also affect this limit. As mentioned, a microscope attachment is necessary for detecting smaller particles and using vibrational spectroscopy, for example. If you have this attachment, you can get down to around 10 microns for FTIR, and actually even smaller in the submicron range for Raman spectroscopy, depending on the exact instrument that you have. If you are using mass spectrometry approaches, there's not necessarily a lower size limit, but instead a lower mass or more accurately concentration that can be detected. This may vary for the different polymer types and will depend on your instruments, but it can also be affected by impurities in your sample that can interfere with the plastic signal. All of these techniques require the use of libraries, reference spectra, or plastic standards in order to accurately establish the polymer type. In some cases, you can use matching software or interpretation software to identify polymer type. When using mass spec, you should also use calibration curves to validate the outputs. The interpretation of outputs from any of these techniques is a really important part of the process. We put a lot of effort into preparing these samples, extracting these particles, characterizing them. This is the last step, but it's still really, really vital that we get this interpretation right. And this is particularly relevant given that none of these machines are specifically designed for microplastic analysis. So it's important to include additional checks such as manual verification of some of the spectra in order to check some of these are correct matches. If you are in need of libraries or reference spectra to help you get started, there are some openly available library files in the scientific literature for both FTIR and Raman. So there's two examples just listed at the bottom here. We have Primke et al. For FTIR and Manu et al. For Raman. These libraries include a wide range that covers all of the common polymer types, but also actually a good range of non-plastic material that might be in your samples. You could have quite a lot of this material left in your sample, depending on the extraction protocol and how complex your sample was to begin with. And actually, a lot of them can look quite a lot like microplastic. So it's very good to have these sorts of libraries that cover some of the non-plastic material as well, so that you're not misidentifying spectra, that you've got the right sort of materials in your library to do accurate analysis. All of the chemical characterization techniques require some sort of sample pre-treatment. This is to remove interferences and to concentrate the microplastic particles. We've already addressed these in the particle extraction session, but it's just important to note that the approach that you select should be tailored for the chemical characterizing technique that you will use. And again, the use of the filter should also be determined by the technique, as mentioned before. Chemical characterization is now considered to be essential for microplastic analysis. Many early studies didn't include this step, but we quickly found out that visual analysis can be sometimes deceiving, and it's possible to either significantly underestimate or significantly overestimate the true microplastic contamination. Without including a chemical characterization step, you should only refer to your particles as suspected microplastics or anthropogenic particles or something similar, just to sort of recognize that you've not undertaken this chemical characterization. The minimum requirement for performing chemical characterization has been suggested as 10 to 25% of the total particles. But this does really depend on the total number of particles that you've found and the distribution across the different samples. If you've only found a few particles, then it's still recommended that all should be analysed. And really the ultimate aim is to chemically characterize 100% of the particles that you found. Then we can confidently say that we have established the microplastic concentration of that sample. Sometimes this isn't feasible, especially if you found a large number of particles and you're following a kind of particle by particle chemical characterization technique, such as single particle FTIR. If you only analyze a proportion of the particles, it's important that you should take a representative selection across the range of different particle shapes, particle sizes, and across the different samples as well. If you find that any of the particles turn out to not be plastic, you should make sure that you correct the overall data for this proportion of non-plastic materials as well. All of these different techniques generate different data outputs. An example of this, FTIR and Raman, the vibrational, they can provide data about the polymer type of each individual particle, whilst the mass spec approaches give the total mass of each polymer type in each sample. The physical characteristics of each particle can be determined prior to or during FTIR analysis. That's size, morphology, for example, during visual analysis. However, for mass spectrometry, typically it's a bulk sample once you've done the sample pre-treatment that is analysed, and we don't have that same physical characterization of particles. So that's another sort of aspect that you should be considering. What sort of data do you want out of this chemical characterization process? And these different data outputs are kind of preferred in different contexts. So policymakers typically prefer these mass-based concentrations where we have kind of milligrams of different polymer types, micrograms of different polymer types per kilogram of soil or sediment, for example. And this is useful for setting targets or limits for microplastic contamination. In contrast to those that study the associated risk, the potential risk of microplastic contamination, for example, ecotoxicologists, they're typically more interested in particle characteristics, where kind of the size and the number of particles and their shape is much more relevant for establishing the associated risk. And finally, we need to consider how to report all of this data. We can report quantitative data, that is mass or count-based concentrations that have been validated analytically, such as with microplastic standards and using calibration curves. We can also consider if these concentrations are above the limit of detection or the limit of quantification based on our blank samples. But we can also report qualitative data, and that is when we can only really confirm the presence or absence of microplastics in a given sample, and then includes some information about the physical characteristics of particles. When reporting concentrations, we should aim to report in multiple kind of units or expressions where possible. If you browse the different microplastic studies, you'll see that lots of different units are used, and this makes it very difficult to compare between different studies. For example, you might see particles, number of particles, or the mass of particles for different volumes or a mass of a sample. If it's possible to include both count and mass-based data, and also for the total volume or the total mass of your sample, this will help to increase the comparability between your study and different studies. And finally, we can also include information about the different polymer types and different particle types and morphologies. This helps to infer about some of the potential sources of some microplastic types. For example, if we report fibers, we can consider different sort of textiles and processes for release to the environment that are relevant for those kind of release types. And also the different information that we provide about the physical characteristics can also actually tell us a lot about some of the potential risks that the microplastics pose to the environment. So it's important to include a wide range of sort of characterization information, everything that you can around your microplastic data when reporting. Okay, thank you very much.
Thank you, Rachel. And we will not have a break right now. We will continue with the questions. First, I would like to say again, thank you, Rachel, and thank you, Nina, for taking us through the details of working on microplastics. We have received quite a few questions. Some of them, I believe, has been answered through your presentations, but we will now go through the questions and try to answer. So, Rachel, we have first a question here, which is, if you don't have an FTIR, what do you do? And I think you have already touched upon it, because you will then not come closer than to a visual characterization, and there is a certain uncertainty to what you can then say.
Yeah, that's correct. Yeah. So obviously not everybody has access to some of these chemical characterization techniques. But just because so many things can look like plastic in your sample, it's not possible to use just visual analysis alone to state microplastic content in a sample. So that's when we have to just use a different term. So we have to play around with something like anthropogenic particles or suspected microplastics, and that's as far as we can get. And just because there's potential for this kind of confusion between, for example, different types of chitin that can be very resistant, can stand up to all of your extraction procedures, and can be shiny and fit all of the categories like plastic. So it is a limitation. And we have seen that some of the early studies, if they've looked again at their data with chemical characterization, the concentrations do change quite a lot. So it is a very important step.
Yeah, thank you. And then my next question goes to Nina. So, and this has also been touched upon by Rachel, actually, and that is how many particles should be determined using FTIR for each sample. And as you say, Rachel, the aim is to look at everyone. But of course, we have also the experience that there may be samples that contain a lot of particles. So what do you do then, Nina?
Yeah, so one of the particles, one of the individuals of a biota, which was a blue mussel, had over 200 particles in it. So what we did was categorize all of the particles, so morphology-wise and color-wise. So all of the black rubbery particles into one, all the red fibers into one, orange fibers, translucent particles or fragments. And then we took a subsample of them. So if we had 50 translucent particles or fragments, we took 20% of that. So we would individually categorize all of them and then see what happens. If we got the same polymer type every single time, we would stop at the 20%. But if we had different, we would continue and see how much of a variety it would be.
Thank you. Okay, then my next question goes to Rachel. And you mentioned the different different matrices and different methods. Some are simple, some are challenging. And here's a very specific question. What would you recommend to use for doing the analysis of microplastics in salt?
In salts, yeah. So the salt it's not too difficult to matrix. We can dissolve the salt into a solution, and that gets us something close to a clean water sample, but there are some impurities in there as well. So the main thing that we want to look at is how impure that sample is. So once you've dissolved it, do you see material settling out or floating to the top that doesn't necessarily look like plastic? Like, are there some sediments in there? Things like that. And this really depends on the origin of the salt and the process that the salt has gone through, and whether it's like edible salt or road salt, for example, because they go through different processes. And then you can either use a filter, which is kind of appropriate. So if you are only looking at particles above, say, 50 micron, and you have a lot of fine sediments or fine impurities that are below that, you could use, for example, a stainless steel mesh that is around 50 micron to allow some of those impurities to pass through, so that you're not waiting a long time for that sort of dissolved salt in the water sample to pass through, for example, a glass fiber filter with a small pore size. You also want to make sure that you really dilute that water, that salt, so that you've really dissolved as much as possible and you're not getting any salt crystals left on the filter paper. Obviously, you want to pre-filter that water to make sure you're not adding any contamination. So pass all that water through a filter paper or use filtered milky water to make sure that there's nothing in addition in there. And then also you want to, once you finish filtering, rinse off the filter paper very carefully to make sure that you haven't got residual salt that's dissolved in water sort of in that filter paper that can then crystallize once it dries.
Okay, thank you, Rachel. And then I have a couple of questions for you, Nina. And yep. A very specific one. Where do we get our reference materials from for spiking our samples?
So the fibers we have made ourselves by washing countless amounts of
textiles.
Blankets. Yeah, textiles and blankets. And then we've collected them, so you can actually see how much your clothes actually shed off. It's a little daunting when you collect all of them. We've also made some of the reference materials ourselves, but also bought some. So these are clean materials that we use so that we know the density of the particles of the fibers and all of the fragments.
Yeah. So then, as you mentioned, we also actually can produce some reference material. And we have done so also for some interlab comparisons where we have produced the reference materials and then organized the interlab. We can come back to that. Another one for you, Nina. Let me see. If you use an agitator, how many rounds per minute do we use?
So for liquid samples, we use up to 125 rotations per minute. But for sediments, we vigorously shake them for about a minute. So it's not very violent because you do not want to break up the existing plastics in your sample. Because if you do that, you actually might create more. So with liquid samples, that's fine because nothing's really grinding against each other, a lot of friction. But you need to be careful when you shake your soil or sediment samples. Yeah, so that's done by hand.
Yeah, thank you. There is one question regarding instruments, Rachel, and I think you have touched upon it because you have shown that there are quite different. There is a selection of different instruments that can be used for chemical characterization. But would you say that there are some that are preferred above others? The question is whether there are any qualifications in choosing an instrument that can analyze microplastics.
Yeah, so it really depends on what data you want out from it, and also what you want to spend and how much time you want to end up analysing it. So you need to consider those things when you are selecting an instrument. If you are looking to provide mass-based concentrations and you're looking to look at levels of microplastic across a lot of samples, for example, to do kind of routine monitoring, something like a pyrolysis GCMS might be more useful because you can analyze the samples a little bit more quickly and you don't get that same particle characterization information, but maybe that's not necessary for a large-scale environmental monitoring where you're just looking at different concentrations. If you want to do something that's more kind of research focused and you want to look at the different particles, then it's FTIR and Raman that are most commonly used. So they have some pros and cons between the two in terms of like the lower size of the particle that can be measured and then how quickly each measurement takes. So Raman, you can go a little bit smaller if you've got a micro Raman, but it takes a bit longer to take each measurement with a Raman, so the FTIR tends to be a bit quicker. So if you're looking to have kind of particle by particle data, then FTIR or Raman is the choice to go for. But there's not kind of one machine that stands out as like the best one, and that's really why we have so many available. That's why so many have been used in the literature, just because they are useful for so many different types of interpreting the data or using the data afterwards. So there's not one that's like definitely better than all the others. You have to consider what it is that you want your instrument to do.
Thank you. Then we will move on, and a new question for you, Nina. Also a very specific one with regard to the procedures. Will it affect the microplastics in the sediment sample when heated at 60 degrees for 2 hours after adding the peroxide?
So some polymers can have some sort of deformities, as we've seen from Rachel's slides. So we usually stop at 40 degrees just to ensure that we have not inflicted any damage to our particles. So some polymer types will be affected by above 50, yes. Yeah.
Thank you. And also then you mentioned our practice, which is of course what this entire course is based upon. Practice
yes,
and the state of art as we know it. There is a question for you, Rachel. I don't know if it's actually possible to answer this completely, but what would you say is the minimum % extraction efficiency for results to be acceptable?
Yeah, so there isn't anything set for that. There's no kind of standards that are mentioned in the literature for what is acceptable. And actually the use of spike samples and investigating that extraction efficiency is only recently being kind of taken up. So when microplastic analysis started out, when microplastic research was a field, it was missing some of these important components of QA/QC. And it's only now that they're becoming discussed as being very essential parts of confirming what is actually in your sample, what did you actually find. So it's still not very widely reported, so we don't really know the full range. We've done it a bit at NEVA, and it depends on both the polymer type and then also the particle characteristics, so the size of the particle and its shape. If we have, for example, a smooth polyethylene bead, then we usually get close to 100% extraction. But for some of the more complicated particle types, for example, quite twisted fibers, we usually get something closer to 80% extraction in total. So we consider this to be acceptable, especially given our experience at NEVA with other types of chemical analysis, that this sort of extraction is considered, that's acceptable, 80% is acceptable. And then we just need to consider that in the data as well.
Thank you. Then we have a question which I believe that you have already responded to or explained, Rachel, during your presentation in session 3, but I will repeat it and then you can see if you'd like to add something. But the question is there any reference to identify the absorption bands, the spectrum used for identification in an FTIR? And I believe that you have already said that yes, there are reference or libraries to help out. So I don't know if you have anything more to add to that.
Yeah, I can elaborate a bit on that. So especially when you get started with FTIR, libraries are pretty much essential to help you interpret the particles. But it's important to remember that you, as the user of the machine, you have more chemical intelligence than that matching software. So that's just an algorithm and it doesn't really know anything about chemistry. And even if you feel like you're quite new to the technique, you definitely know more than that algorithm does. So it's just looking for peaks, and it's just trying to match those peaks and the areas underneath the peaks, and it doesn't always work. So you want to use that library, use that as a basis for identifying a polymer, get to know some reference material, analyze that, see what the spectra look like, and then you want to do kind of your own manual verification of those spectra. And there are guides available on the internet and book chapters and things like that, where they talk about what goes on at the different wave numbers on the FTIR spectra, so what different peaks mean, and so you can then confirm whether your library match is correct based on, okay, yes, it has that band in that place, so that means that it is that polymer type, or hang on a second, this really important band for that polymer type, that's missing, so this library match, that's not correct, we need to look into this particle a little bit more. So the libraries are extremely useful resources, and the ones that are available online openly are very good, but you need to consider them as a starting point and look into more detail with your spectra as you get used to your machine a little bit more.
Thanks a lot. I see there are more and more questions coming in, which is good, and we will try to make our answers short so that we can answer most of the questions actually. This is now a question that goes to sort of both of you, and I think we should try to be short on this, and it's not really about our methods, but could the microplastics actually be reduced within the organisms? I suppose that this is a question about degradation.
Yeah,
do we have any
so
knowledge on
try
this?
and remove them from the environment? Is that what the question? Is that to remove the particle?
I interpret the question as if there may be some kind of a biological degradation within organisms. Do we know?
Oh, right, once they've been ingested.
Yes.
Yeah, I mean, that is possible to damage the particles or degrade them. We have seen that in earthworms, where there's actually a lot of sand in the digestive tract. And as the kind of worm moves along and we see these waves of movement down the worm, and that this digestive tract gets sort of twisted, this sand just even mechanically can grind up the particles and generate smaller fragments. And other examples, we see that once particles have been ingested, they end up being fragmented in the gut when there's exposed to, for example, different enzymes or different microorganisms in the gut. This might not necessarily be actual biodegradation of the polymer, but sometimes of the additives that kind of hold the monomers together. So sometimes it's kind of weakening the polymer and then fragmenting it. Other times it may be biodegrading it, but there's often very specific examples of this. So it's only a few polymer types in very specific settings. So it's not something that happens very widely.
Thank you, Rachel. And I will continue with a few questions for you, Rachel. The question now is if there are any non-destructive methods for analysis of microplastics.
Not really. So FTIR could be considered partially non-destructive, but because you can sometimes take your particle back afterwards, but the techniques that are often used to get the best possible data involve crushing the particle, squashing it to try and reduce any oxygen layers that are between your sample and where it's being analysed, and also to reduce the sample thickness so you get very good transmissions data or reflectance data, for example. And so if you want your particle exactly the same, that's not what you're going to get. If you use Raman, the lasers can burn the particles and they are lost, and pyrolysis, GCMS or other forms of GCMS, they obviously destroy the particle. So there's no single chemical characterization technique which will just leave your samples completely fine as they were before. So yeah, you have to keep that in mind. Yeah.
Okay, Nina, and the question for you, I think it's possible to answer this quite short. You said you were talking about the color scheme of when you identify particles, visual identification, and the question is this saying something about sort of the life cycle or the age of the microplastic particle? Do you have any knowledge about this?
It can, but it also can't. I mean, if it's degraded but through UV light, it can actually be weathered, and it goes from brightly red to almost pink. So yes and no. The point of categorizing the particle by its color is to make it easier to actually identify it later on as well, to see how many particles of that same color, of that same type of morphology, of that polymer type will be in your sample.
Okay, I'm moving back to Rachel now. We're talking about the extraction and chemical treatments. Which one would you say gives the minimal damage to most polymers?
That would definitely be enzymatic digestion. So when we use enzymes, they just target the specific form of organic material that they're able to digest. So we can use cellulase, and that just attacks cellulose. If we use proteinase, that just attacks proteins, and so on. So long as the protocol that is used to add those enzymes and to do that enzymatic digestion don't include additional chemical treatments that can damage the polymers. So sometimes acids are used, for example, to pre-treat cellulosic material before cellulase. As long as we don't have that kind of protocol when we use it for microplastics, they should not affect any of the polymer particles. We do find that other approaches are also very safe because enzymes can be expensive and time consuming. There are cheaper and quicker options, but you just need to keep your mind to the temperature, the concentration, to make sure that they're not dangerous to the particles.
And I will follow up with another question, which is sort of similar to this, and we have touched upon it already. It's about analytical methods to detect microplastics in consumer products and food. And yeah, you have mentioned it already, but maybe you will elaborate a little bit on this, Rachel. What would you say are the best when we have these kind of complicated matrices?
I think it really depends on the chemical characterization technique that you use. It might be if you have a certain type of food or drink sample that you can get away with a little bit less sample pre-treatment if you're using a mass spec approach, for example. So you want to look at other types of analysis that have been performed on different types of food and drink, because it might be that you don't need to go through as many chemical pre-treatment steps to handle that material. So for example, that material might not interfere with the plastic signal when you're using mass spec techniques. And that's something that you just need to look into the literature. It's not something that we've tried at NIVA yet, so we don't have anything concrete to answer on that, but it might be that you can skip some of those steps. If you're looking at in food and drink, especially for human consumption, as I mentioned before, there's still a lot of unknowns with that. So it's good to have a look in the literature, and then to also, most importantly, is to get hold of some of that material and play around with it with some different digestion or extraction protocols to see what works.
Yeah, thank you, Rachel. I will now go back to one question. Let me see. There's a lot of interesting questions coming up here now. Again, Rachel, there's a question here. After the FTIR analysis, can we use TGA analysis?
If you if you make sure that those plastic particles are retained, because it doesn't really matter if they've been squished a little bit for TGA, you can potentially retain those particles for TGA. That's correct. So it depends on the analytical mode that you use.
Yeah. Then I got a question here that I actually think that I can respond to. And the question is, maybe have a copy or link of the publications of your research, especially for biota samples. And I would say that yes, after this, it is possible to provide a list of our publications. Of course, scientific publications are available by different search engines, but we do have also quite a few reports that are maybe not that easily accessible from search engines, and yeah, it is possible after this to provide some examples of these reports and publications. Okay, I will now address Nina with a question, and this is also quite specific to what we do in our lab. And why not use pure white instead of colored rubber tubings?
That is so that we can see if there's been any type of friction and contamination into our samples, it's very visible to see in our samples. And that is why we have fitted brightly colored tubes to our equipment. And it's also important for us, we've cut a bit off and looked at them through the microscope to see, to investigate and to have like an idea how they would look like in a sample, so that we can visibly see that in our sample if we have contaminated. Yeah.
Yep. Thank you. And also just to follow up, so because there might be some white particles, right? So that if the tubing was white, then it was a larger chance that you will actually mistakenly taken it as a microplastic particle from the environmental sample and not from your surroundings. Yeah.
Yes, that's correct.
The filter paper is white, so it's easier to see the colourful particles. So it's easier to spot those.
A good argument. I think I will now take one question that we can actually all three of us respond to, and the question is there a standard or a criteria for an environment to be considered polluted by microplastics? And of course this is a very relevant and interesting question. It's not directly to our method, but an environmental quality standard is not yet set for microplastics in the environment. I would just like to mention that there has been quite a large study in Norway trying to compile international studies that has been looking at effects, and the purpose was to try to define the PNEC value, the predicted no effect concentration for microplastics. And actually the study included more than 2,000 papers, and after a very thorough quality control of these papers, actually approximately 10% had a quality that was set by this group of scientists that were looking into the papers. And they did try to come up with a PNEC. It's not a standard. Do you have any additional information, Nina or Rachel?
Yeah, I could add that when we use the word polluted, we obviously mean that that means that there is an effect, an observed effect. So before we actually have seen an observed effect, which we haven't really got concrete evidence of in a wide range of environments, we use the term contamination. We've seen that pretty much everywhere in the world is contaminated by microplastics. So even a recent study showed that it comes down in the rain in very remote regions. So we can kind of identify pretty much most environments as being contaminated by microplastics. And until we have that effect that we've established there is a negative effect, that's when we can kind of introduce the concept of pollution and polluted environments.
Yeah. So still a way to go in this aspect. Okay, so a very specific question again, back to methods, Nina. And the question is, when considering your sample blanks, if you actually find any contamination of these, what's the next step? I think you touched upon it, and also Rachel, but what do we do?
So the next step is for our samples is to identify if we've got similar contamination in our environmental samples, and that will then be recorded, and according to whatever way you would like to deduct your blanks from your samples, that's how you proceed. So it would either be remove all of the samples, or remove all of the particles from your data that looks exactly like what you've got. But if it's cellulose, you would probably not want to have that in your record, your raw data anyways. But if it's another way, you can go for what Rachel's mentioned, which is the LOQs and LODs.
Yeah. Okay, thank you. Let me see. I have a question for Rachel here now. And again, back to extraction and digestion. And there are some specific questions. So we have to think of what we have experience of and have also knowledge about. So could you give any recommendation to an effective digestion of carapaces of shrimps or crabs? Have we
that's something that's very difficult. So there is a PhD student who is part of she's doing a PhD in NEVA, and she's looking at microplastics in freshwater macroinvertebrates, and it's the chitin in the carapaces that is very difficult to remove. So when we have chitin, that is very resistant, and using chitinase is quite expensive, the enzyme that attacks chitin, and also it needs to be optimized for your samples as well. The PhD student, Amelia, she's done some really great work looking at different approaches. So you can pre-treat your samples with some hydrogen peroxide, which kind of weakens them a little bit to improve the chitin treatment. But something like hydrogen peroxide alone, all you're going to do is bleach your samples, bleach the chitin, or potentially just leave them completely kind of unaffected by the treatment. So that one is a pretty tough one to deal with, and there's not there's not protocols that have been published yet that really effectively address that. So that's still one of the tough ones to deal with.
So also the one that raised this question said that they have tried KOH and it didn't really work.
Yeah. I think a lot of them will not really work. Yeah.
Nina, you would like to add something?
Yeah, just a note to using chitinase. We've also figured out that if you've got stored samples, if you stored your organisms in either ethanol, formaldehyde, some sort of preservative, that can actually also affect the process further on. So it could either increase it, or in our case, it can stop the process of degrading the chitinase. Yeah, so that needs to be considered as well, what the organisms are actually being preserved in. Okay.
I think we can take the time for one more question, even though we are a bit on the schedule, but the last minutes with conclusion and closing will not take that much time. So there is a question here, if you could explain more about the FTIR identification process and how to prepare the samples before we go to the micro FTIR in terms of filter papers or sample holding kit. Is this something we can try to say in just 1 minute, Rachel?
Sure. So very briefly, it depends on what analytical mode you're going to use. For example, if you want to use transmission mode, you need a filter material that the IR beam will pass straight through. If you want to use reflectance mode, you need something that is IR reflective. So something that is IR transparent is, for example, silicon. That doesn't impact the spectra too much. Something that is IR reflective is silver. And those are both available for purchase as microplastic filters. So you want to take all of your sample pre-treatment to concentrate the microplastics and remove sediments and organic material. And then the final step is to filter onto that relevant suitable filter material.
Thank you. And by this, I will close the questions and answers session. And I have a few closing remarks. So I will share my screen again. And this is the right one, I believe. Excuse me, just a few seconds. Okay. And I hope that most of the participants find that this has been useful, and also that the questions you have raised has been answered either through the sessions or now after. There may be a few that we didn't have the time to come into. What I would like to say now after this, that there is also a possibility for us to continue and to develop the training program after this. So after this now, CSEAS will send a post-training questionnaire to all the participants. and ask for your evaluation of this course, and also request your interest for taking part in a training program that follow after this introduction course. And there are two kinds of training that we have the possibility to offer and provide. One is demonstration videos presenting the analysis of microplastics step by step, and in a few seconds I will show you an example of such a video. And following these videos, we can also provide some exercises and have a workshop to discuss your experience and challenges, and to support you in the development of potentially your guides and protocols within your institute. The other training that has already been mentioned is sort of a training, but also an important step in the standardization and harmonization of methods. That's an interlab comparison, an ILC, or microplastic analysis. And given that we actually produce reference material, this is something that we can set up and arrange for interested participants. There have to be a limit to the number of participants, but this is something we can come back to when we know the interest for taking part in such an ILC. And in this ILC, what we do is that we provide these reference materials, and the first step would be to identify the polymer types using pre-production pellets, and then quantify the number of microplastics of different polymer types. The next step would be to analyze the spiked matrices of water and sediment for microplastic particles. So these are possibilities, and we will develop this when we have seen the evaluation of the course and your response to the questionnaire. So now I will spend a couple of minutes just showing you what these demonstration videos could look like. It takes 2 minutes, and I hope you have the time to join us to look at this. And I also hope that this works. And let me see, it should work now. Okay, I got a response that this was not flowing properly, so I will stop sharing. And unfortunately, it didn't work out, but anyway, our message is that it is possible for us to provide this kind of videos. And what they do show is a step-by-step process for actually doing the microplastic analysis. But we will come back to that. And now what's left actually for me is to say thank you all for participating in this introduction course. It was an interesting experience for us, and I hope it was of value to all of you. And don't hesitate to make contact also directly to us if there are any questions that you would like to discuss. But first of all, I will encourage you all to respond to the questionnaire that you will receive. Thanks a lot.